Hope you are doing well. Welcome to Leetcode Solver. Today we are going to solve 21st problem in May Leetcoding challenge, and the problem name is count square submatrix with all ones. Given M cross n matrix of ones and zeros, written how many square submatrices have all ones. How many submatrices have all ones, which should be square? Well, we had solved this problem, similar problem before, which asked us to find the maximum size of the square in 0, 1 binary matrix. So we can utilize the same idea. Here we will focus on counting total number of square submatrix instead of finding the one submatrix which is maximum. Well, in that case, we have calculated the size of like in every point ij, we will be finding the well, we have a dynamic programming solution we had, which will in every point ij, it will find the maximum size of submat submatrix square ending at ij. Or ending at ig can be rephrased as having uh, bottom right corner at ij. Well, basically, if we interpret this in figure, then it will be something like this is 1, this is 1, suppose this is also 1, 1, 1, 1. This is our matrix, and in this position, say this position, the value it will contain so will be 2, because the maximum it can go to the left side. This is like 2 from here, because this is being uh, limited by the square in its up position. So basically, this answer at this position will be 2. This is the submatrix we can draw, which is of size 2. We cannot draw submatrix of size 3. So this position, it will hold 2. This is our ij, and this ij will give us 2 here. But if we had something like another row as well on the top, 1, 1, 1, in this case we see that we can form a submatrix which is of size 3, because we can get same from like to the top as well as to the left side. So how we had calculated this answer for each ij? The answer for each ij can be easily calculated by what is the maximum size of square which end up to this position. Like up to this position we see, although we have 3 to the left, but it is limited by 2. So up to this position we see the maximum size of the square we can form is 2, and up to this position is also 2, because of the same reason, although it have limitation of it can expand to the top side here, but still being limited by the value to its left sides. So we see the maximum square submatrix ending at this position is 2, at this position is also 2, and the maximum size of the square ending at this position is also 2. So we can have our submatrix ending at this position by finding the minimum among these 3, but the minimum among these 3 is 2, and adding one more value, so the answer will be 3, 1 plus minimum of all consideration. We have to consider these three consideration. We have to consider these three because it is I mean this is limited. The left upside is limited by this value, and our left side is limited by this value, and the top side is limited by this value. So we have to find minimum among this and add 1 to this value. If it is 1, then if it is 0, then no consideration of submatrix ending at this position. Well, in case if it is not, if it was not there, then the maximum square ending at this position was 1, and maximum square ending at this position was 2. And the maximum square ending at this position was also 1. So among the three, we have 1 as our maximum one, minimum one among these three, which is basically the limitation of these three. So limitation of these three plus 1 is our answer here. The answer is 2. So 1 plus minimum consideration is 1. So answer is 2. Well, in this way we will solve the problem. The time and space complexity both, well, for the time complexity, big of n is n cross m, where n is the size of the row and m is the size of the column. And for space, we also have to use m cross n, although we can minimize our space complexity to as we do only need 2 rows, because we don't need further rows information as we progress. So we can have complexity of 2 cross column, which is also means that we can have our space complexity as a column, size of the column. Well, let's go with the complexity, which I mean we can optimize the space complexity later, but initially let's go with m cross n complexity, row cross column complexity. Let's define the row as a matrix dot size, and if we found that row is empty, then we'll return 0 as the answer. Otherwise we will calculate column, which is equal to matrix 0 dot size. Now if we found that column, let's define a vector, and for storing our result, vector. This solution is also called dynamic programming. Let's define as a dp, and we have row by column dp column. Initially let's put everything 0, and let's iterate over our matrix. Now if we found that matrix ij is 0, then we have nothing to do. We'll just continue loop, and otherwise if we have I is 0 special case, or j is 0 first row or first column, in that case we will have dp of ij equals 1, because we already skipped the matrix which has 0 value, which will add nothing to our solution. And let's go with other cases. If it is not corner row or corner, I mean the first row or first column, then we have to find the answer. Else the answer will be, let's define minimum side size, which will be equal to minimum among these three sides, which is dp of left side. Let's define dp of I j minus 1 left side, and minimum of we have two other furthermore dp of I minus 1 j, which is the top one from current position, and the diagonal one dp of I minus 1 j minus 1. So we will find minimum among these three sides, and we will update our dp to that value. Dp of ij will be equal to 1 plus minimum side size, and finally we will update our answer. Count 0, we will update our answer. Count will be equal to dp of ij. The size itself will determine the total number of square. If square is have uh, size 2, then we can form two submatrix ending over here, which is of size 1, which is of size 2. And if it is 3, then first the square ending up to this position is of size 1, of size 2, and of size 3. So basically the size itself will determine total number of count of the submatrices of square submatrices itself. Well, finally let's return count. Okay, all right, let's submit the problem. Solution accepted. Okay, all right, this is a big of n cross m solution, and hope you like the explanation and solution approach. We can also optimize our space by just writing 2 here and just determining if it is first row, even row, then we will put it in a 0 index, and if it is odd row, then we will put it in a 1 row of the index. So which we can do easily by I. If I is 0, then we will simply, or j is 0, let's I mean we can simply do kind of, I mean, like if it is even, then make it 0, if it is odd, make it 1, which can also be done something like finding I modulus 2. So if I modulus 2 is 0, that means it is a even number the same way, and I modulus 2 is 0, that means for even number we are putting in a 0th index. So we can do simply I modulus 2, and for everything I modulus 2. Well, I minus 1 modulus 2. So we all know that I modulus 2, which will give us modulus by after dividing by 2. So if it is even, then it will give us 0. If it is odd, it will give us 1. And for every even row we are making 0, for every odd row we are making 1, so that we can easily have the information of our previous one, and we can do the further calculations. Well, let's run the code. Okay, all right, let's submit. Wrong answer. Maybe we did something wrong somewhere. Two, it is 1, 1 minus 1, 0, 0 modulus 2, 0. Okay, we have to make sure that we have made everything to 0 initially. So if it is a 0, then we have to make sure that it is 0. So for that, let's make I modulus 2 as 0 initially. Compulsion error. No variable overlap. dpi modulus 2 equals 0. What? Equal suppression. Oh, sorry. J. Let's submit because we have not initialized value again. That's why it was causing error. Here we have to initialize value. Some value may persist previously, and we are skipping if to update if it is 0. That's why. Well, thank you so much for watching this video, and see you in the next video.